Yeah, okay, so let us start. So welcome to the second talk. And so yesterday, I illustrated how to capture the entropy of black holes from the boundary field theories, n equals 4 by Yang-Mills. And in particular, we constructed the saddle point of the index matrix model in the Lorentzian limit, which is dual to the supersymmetric black holes in AdS5 X S5. And one natural question you can ask is that, so what did we count? I mean, what kind of operators we counted yesterday? So can we really explicitly write down such operators dual to the black holes in the bulk? So this is what I'm gonna talk about today. So in a sense, you can think about it as BPS version of the bulk reconstruction. I will show you an explicit and quantitative map between the quantum states, especially the black hole states in AdS, and the operators in the boundary CFTs, thereby reconstructing the bulk AdS quantum gravity spectrum. And for that, we'll use the language of supercharged cohomologies, which I will explain now. So let us begin with very brief introduction. And, graviton, or when I say graviton in today's talk, I mean all perturbative particles in the bulk, including not only gravitons, but also photons, scalar particles, or fermions, and so on. So these perturbative states in the bulk are well understood. Then my question is, so what's so special about the black hole microstates compared to them while they are both fundamental degrees of freedom of quantum gravity? And from these black hole microstates, how does emergent geometric description like event horizon arise from them? Or can you understand holographic property of them? Or can we analyze maximally chaotic behavior of them? Can we resolve black hole information paradox studying those black hole microstates? These are all interesting questions. So in order to approach to this question, I will first show you how to construct these operators from which are dual to the black hole states from the gauge series. So my goal is that to convince you that this type of operator, this type of simple operators in the gauge series are dual to the perturbative particle states in the bulk, while these type of operators are dual to the black hole states in the bulk. So if you can understand or okay with that, then today's talk is done. So, unlike yesterday, we changed a bit about our target. So, today also we'll focus on the strongly coupled gauge theory. And in order to do so, we will again focus on the BPS sector. And in the BPS sector, as is well known, certain operators are protected. So we want to study such protected operators. But today, we'll focus on the finite and gauge theory. It is not because we really want to study finite n, but we'll study from finite n, and our ultimate goal will be to approach the large n, scaling with scaling energy of n squared. So at finite n, Newton constant proportion to 1 over n squared will be finite. However, I will show you today that even such a theory, we can somehow distinguish between graviton and black hole states, and these finite and black hole states can be thought of as some quantum black holes in AdS. And the interesting point here is that even at finite n, these states, or these states, these quantum black hole states, they exhibit certain properties of semi-classical black holes we can learn. So let us begin. It's hard to see. Yeah. Okay, so it's the same slide as I showed you yesterday. So we will study to be string theory on AdS5 times S5 holographically from 4D equals 4 SU and super envelopes. So again, we want to study 16 BPS operators. These operators are annihilated by our chosen Poincare supercharge and its Hermitian conjugate. And these Q and Q dagger are nilpotent operators, and their anti-commutator is given by these. So our 16 BPS operators have vanishing this charge combination, meaning that they satisfy this BPS condition. And their energy will be given by the sum of R charges and angular momentum. In the free theory limit, when G is 0, you can read off which kind of elementary fields satisfy this condition. We will call them as free BPS letters, and you can find 3 scalars, 3 chiralinos, 2 gauginos, and anti-self-dual components of the field strengths. And also you can act arbitrary number of holomorphic derivatives of them. So basically, with these free BPS letters and combine them, you can construct general gauge invariant local BPS operators in the free theory. Okay. Then we want to go to higher loop, let's say at wall loop. The QQ dagger anti-commutator is known to receive quantum corrections at one loop order. And the thing is that lots of BPS operators we constructed in the free theory, combining these free BPS letters, acquire non-zero anomalous dimensions at one loop. So lots of them will be just lifted at one loop. And long ago, stress here, and we had a conjecture and we had a belief until very recently that there will be no further corrections. These wall loop order BPS operators will be there even at strong coupling. And there are known examples that this conjecture is true. They are SYK models or the D1, D5 system. You can confirm that this conjecture is true. If you find some wall loop BPS operator, then they will be at the strong couplings, even at the strong coupling.
Okay, just a sentence. Why is there some anomaly there? Why are they one loop itself? But it turns out they're not. So
turns out they're not. But you can find some nice example, but they, yeah, it's true. But generally, it's not true. That's what I'm gonna say. However,
just to say, I mean, if you can relate the anomalous dimensions to some R charge or something, it is nothing like that. It says it's okay.
Anomalous dimension, anomalous dimension is not, this is not quantized charge, so you can be renormalized and get corrections. So an explicit counterexample of this conjecture has been very recently shown that in this paper, people suggested that 16 BPS sector of 4D equals 4 SO7 superyoung. There should be some kind of higher loop corrections on these BPS operators in order for to make SGLity consistent. And Unu here and his colleague showed that actually he find an explicit example of this 4D equals 4 SO and superyoung mills that you can find a pair of all of BPS operators which are lifted at two loop order whose correction was inferred from the generalized condition. So even if we construct some BPS operators at one loop order, they can be lifted at higher loop order.
And maybe one thing that this counterexample was found from the idea of Abhijit and friends, right? That
Sure. Yes, that should I have mentioned. Sorry.
Well, the idea was to, I mean, it turned out it's not necessary because it's getting lifted, two loop order itself, right? So if one could do a two loop calculation, one would have found it. But what we had in our minds is that maybe this conjecture is true to all loops, and maybe the non-portability effects would be culprits, if at all. I mean, if at all, that was also not clear whether that will be the case. And so the idea was to check it against S2 ability. So we know that N equals 4 SP3 theory. This dual N equals 4 SO7 theory. Right? So if the one loop conjecture is true in both theories, then one loop here should match with one loop there. So it's some sort of a cheap conclusion that one draws from one loop non-normalization, and which allows you just calculation of one loop on both sides. So we did the calculation SP3 side, and we came up with we proposed a calculation SO7 side, which could definitively check whether this conjecture is true or not. Which is what we did not do that. Which is what Chang and Lin did, and saw that it is not matching. But later, just recently, Wu and Jeo, they saw that it's just lifting a two-loop.
Yeah.
So both the conjecture and the counter examples that we have.
No, that's great to know. And I'm sorry to slow you down, but so when I worked on Suzy N equals 1, I used to know the permission harmony. It has to be replaced twice for any anomalous dimensions and so on, right? But is there an actual anomaly that is the basis of the two anomalies as we normally understand them? At the root of the two-loop effect? Because that might allow one to. Yeah,
Sure. Maybe I didn't understand. But
What is the anomaly? What is anomaly?
what is anomaly?
yeah.
So the Konishi anomaly is a supersymmetric generalization of ADJ anomaly. So you have a U1 axial symmetry, and then at classical level and at quantum level, that U1 axial symmetry is broken. And in n equals to 4 polynomials, there is no such U1 axial symmetry. So actually, the symmetry is already broken, but the effect is still there because maybe the best example is Payan effective field theory. So there, even the mass term, even Payan has mass, so that it breaks U1 axial symmetry. The effect of APJ anomaly is still there. Right, that is important in decaying process, right? So here, U1 chiral is broken, but the effect is still there. So yeah.
And what? There's the SO6, which of course is different from this U1 you're talking about.
Mm-hmm.
Now SO6 is SU form.
SU4, yeah.
What if this U1 have made SU4 U4? That's what I know.
So this U1 symmetry is rotating phi to e to the I alpha phi
For all phi's.
for all phi's,
All chiral phi's or
all chiral phi's, but not rotating theta. So rotating theta is a U1 arch, right? But theta is to remain non-uniform, and only phi is. So I don't know whether it can be
Not quite part of us.
not part of all.
So, but if you just look at section on phi's, then it's kind of like you SU4 or SU3 becoming.
Yeah,
I'm so sorry. But just, does that suggest that, the effect would be more general than something as specific as SO7, something? If it's as.
Yeah. This is just a first counterexample, and there can be some other.
So what do you say about that in paper for SUN also?
we don't know. I mean, like Konishi anomaly is there in that theory as well.
Yeah.
But we don't know whether Konishi anomaly can lift.
Well,
Because
I
we don't
thought
have that
the
example.
lifting simply is that something is related to something else using supersymmetry. It's really lifted, right?
Right, but like we don't know whether. So maybe it is logically possible that already one of this all the bridging test operators and like pseudo test
Okay.
don't go. That's
Also, that is another question. So why is it happening at two? Anomaly effects happen. Even if there is this anomaly in this broken symmetry, would have expected to happen at one lead. Right.
I think this is like so if we call this one loop as free level,
this was free level, right?
then anomaly is one loop bit back, and I think that's just
That's just a language.
Oh, so it's the same. It's a one loop that's
It's one loop. It's one loop in normal sense. The other one is one.
Yeah.
Yeah.
I see.
Yeah, one loop to Q. And here one loop is Q dagger. So
Yeah. The order G is easier to say.
Yeah.
So order G cube.
So order G has Q G squared.
G squared to Q.
Order G squared.
To Q. Yeah.
The tree level has Q proportional to G. And here this anomaly has Q proportional to G.
Just G squared. Right.
In Chinese paper, there's a comment. There's a comment about SU2 case. They found this explicit example, right? This for Twitter state. They have explicitly stated that they don't know whether it will get it will pair up with some operator or not.
SU2 doesn't get.
SU2 doesn't.
Yeah. So for SU case, I don't know if there's this pairing up going on.
SU2 doesn't.
But this is interesting, right? So with the fact that usually when one talks about anomaly, I usually think of that first of all, zeros order, there should be symmetry. And then I'm looking at the anomaly that's symmetry. But here somehow the effect comes from a symmetry that is not there. It was there in the free theory when coupling was zero, right? Then it had anomaly, and then you explicitly break it by interactions, like n equals 4 interactions. Even then the effect of that is there. So have you seen consequences of such things?
Yeah, as he said, Pavan example is only one I really know, but there, because you can turn off currents and keep breaking, and then you still have this ADJM and all.
Yeah.
And because if the clocks have zero mass, you still have ADJM. So I think it survives in the parallel again, even with it mass. But here, right, it seems like G is playing some role like that, right? Like, like G is
playing the role of the mass.
You have that anomaly, then you have finite G, but it seems that seems to be.
Yeah.
By the way, in SYK and D1D5, how do you make sure that there is no high correction or non-correction?
Yeah, I don't know very well, but as far as I heard that they explicitly matched that wall of BPS spectrum with the strong BPS spectrum, strongly coupled in the strong coupling.
I see. So one can do the calculation on the strong coupling side.
Yeah, maybe from the dual side, holographic side, or.
This is done at very large end then.
Yeah, it should be. Or well, sorry. I should not make any strong thing. Maybe they consider finite that I don't.
But this is SYK is just quantum mechanics. So
Maybe you just compute it.
Yeah. And like the only fight is 2D system, so there might be some nice problem.
Maybe it's like instant or modularized. It's instant or sigma model of this instant or modularized is even at strong couplings.
Right. But cohomology calculation will be very hard.
Sorry?
For this nonlinear sigma model. Like,
maybe not, right? Sometimes you can, in these nonlinear sigma models, you link supersymmetric states to some forms, some harmonic form, and maybe in the space that is okay. I don't know. I mean, it's conceivable.
Yeah, so in this series, you can compare with the strongly coupled spectrum. But yeah, anyway, so n equals 4, we now know that at higher loop, the operators can be lifted. But nevertheless, we have seen that the index correctly captures the entropy of black holes yesterday, meaning that there should be a macroscopic number of protected operators responsible for the entropy of BPS black holes. And these operators will be holographically dual to the microstate of BPS black holes. So not all the operators are lifted. There should be many macroscopic number of them to account for the
majority.
Yeah, sure. And our strategy is that we should construct the candidate BPS operators dual to these black hole states at one order.
But majority are not real.
Sorry. When you showed that plot yesterday, there was this graviton stuff, and then it seemed to agree with the plot with black holes, right? Or was that wrong?
Yeah. But let's say that if you compare the free counting, then both the free counting and the strongly coupled counting have n squared times function of charge, but the coefficients are. So when you have e to the power n squared with a different coefficient, most are different. So between free and interacting, certainly most.
Yeah.
Now between one loop and fully interacting, who knows?
That's true.
So you e to the just the coefficient of the n squared part is different.
It's different.
Yeah.
Roughly, it's like a free box.
Yeah.
Okay, in your plot somehow you had that. I'm remembering one plot. You had plot number 3, first where you put some chemical potentials to be equal, whatever, and then there was some graviton mass, and then it settled to some.
Yeah, it's true that, that's what I mean. There will be many states in the 16-bit sector to capture the black hole entropy. But
it's not.
It's not clear compared to the one loop.
Yeah.
Not yet. I think it will soon be clarified.
I see. The one loop hasn't been computed.
Very difficult. I mean, what Unruh correctly points out, we should call treatments.
So our strategy is we shall construct candidate BPS operator to build to the black hole states at one loop order. If we are unlucky, maybe they will be lifted, but some of them will be there to account for the black hole entropy, right? So we shall construct it first at one loop order and see whether it is okay or not. So one loop order BPS operator, they are analyzed by Q and Q dagger, which means that they are harmonic forms of Q dagger anticommutators. Since Q and Q dagger are the nilpotent operators, you can think of it as some derivative operators, meaning that you can regard it as Laplacian. Then by standard Hodge theory, the harmonic forms can be there. We can find the one-to-one correspondence between the harmonic form and the cohomology class. The cohomology class by supercharged Q. The Q cohomology will be the non-trivial element of Q cohomology class will be the operator that is annihilated by Q, which means that it is Q closed. But the operator that is not written as the Q action on some other operator, which means that it is not Q exact. So this is the non-trivial element of Q cohomology class, and this will be there will be a map between this and the 16 BPS operators. And the benefit of studying this Q cohomology class rather than directly studying these harmonic forms is that because Q cohomology class, 16 BPS operators at one loop can be read off from the Q cohomology class at tree level. You just run on the G Yang-Mills, and from the classical Q action, you can read off how Q act on the letters, and this will give you the tree level Q cohomology. And you can map this to the wall of BPS operators.
So at least this gives you an upper bound on the number of sources. That is still true, right?
Yeah, sure. So these are the classical Q action on the free BPS letters. So phi and lambda are still Q closed, but now you can see that Carolinos and field strengths and derivative are transformed under the Q action.
But can we have a modified conjecture, given that this calculation by Newton's, that perhaps you do this, and then you also do a one loop calculation. I mean, one loop meaning two loop, whatever. Right? And then look at the effects of the anomalies lifting these things. And then the claim is that that is protected.
Because it's an anomaly, it works at one loop and then it's exhausted.
So you mean two loops? Maybe, yeah.
What is your opinion?
I mean, we originally conjectured like that, right? We thought like, but I don't know, like it's.
Yeah, so this has duality setup that is checkable.
Yeah.
So in the operator sense, two loop and cohomology sense, one loop exact. Maybe they will be our new conjecture. Yeah. Also, at one loop order of Q, not only cognition anomaly, but other anomalies can happen. I mean, can enter to this, right? So
By the way, this Konishi anomaly always confuses me. So can I just think of this as any anomaly, any sort of an anomaly in some symmetry, right? Some global symmetry that was present at zero coupling, right? And then Konishi means just its supersymmetric partner.
well, I'm not sure what is. I think people are abusing the word, so I'm not sure what Cornish anomaly really means. Some people use it very strict sense, and some people very broad sense. I don't know.
For me, the main thing in the newspaper was this point that in the 116 PPI sector, you have singularity.
Yeah.
Which is unlike, let's say, 18 PPI, chiral ring, where because dimension of operators given by charge, if you know the dimension of operators on the left-hand side, you know on the right-hand side. So the the charge of the operator on the right-hand side, therefore dimension of operator on the right-hand side has to be greater than the dimension of the left-hand side. Because PPS bars, and then there are no singularities. Here, because, as Rubu points out, because position dependence can also carry J, BPS bound involves J, the argument fails.
So and what? So then what?
So now that opens our whole kind of. Because you see, the reason that classical calculation is not failing is not a ring, it's because of these singularities. Because the singularities can then combine with subleading things to give new effects. So then, I feel this phenomenon seems to persist beyond. Keep going. So I worry that it's a whole new problem.
Yes. So something like just
So it really is something new.
Yeah. I mean, maybe it can all be accounted for, as you say, by tools, but it's not clear. It could just be now totally.
I think one more comment is that you say 1/8 BPS, but there are 1/8 BPS, a different type of 1/8 BPS.
Yeah. I mean, kind of.
Yeah.
And there are different type of 1 BPS. It is.
No, when I say, I just mean the guy.
Yeah.
In fact, that operator is important in this recombination. 1/8 and 1/16 they combine, right?
Yeah.
One of the primary operators.
Actually, one of the current.
Oh, one of the parallel operators.
Yeah. The point is that you can have Q on something 116 be combining with something that's 1/8. So the action of Q on the 1/8 itself will be key. Now, there may also be, but so the Q exactness again we move on. Q exactness from 160. But I was just giving this as a counterfactual. Suppose you've got you don't have any more superstructure, nothing involving J, just charges. Then that is very clean. Because in that sector you don't have singularity flow. Now I think what Rumbu's pointing out is that could be that there's a singularity in the OP in some other sector, which then nonetheless impacts this.
But can you take a little more concrete the fact that there are singularities in OP and whatever this is in conjecture, one good conjecture?
I think that you can understand Rumbu's anomaly.
Please.
Yeah. So let's say that you want to see that first let me give you an analogy.
Yeah.
The analogy is 2 dimensions. If you look at a chiral current. Okay. The chiral current is anomalous. Why is it anomalous? One way of thinking of it is let's point split psi and psi. Psi and psi. Okay. And then put an e to the power I A. Okay. So now you look at this thing, bringing down the delta x times A. As you take delta x to 0, the delta x times A is irrelevant because you're taking delta x to 0. Okay. However, because the two of them have a singularity in the OP, the delta x times A can combine with the OP singularity to give you some finite. And it changes the del mu J mu. That's something extremely similar happens in Rumbu situation. Extremely similar.
Actually, I think they're the same.
Yeah. So it's just this. I think this could not have happened without singularities. So the fact that these OPs are singular is somehow at the heart of it. And then this worries me that it's like just different from classical problem in a more general way. Because the whole field, you think of this like as a two plus one dimensional field here. Because you've got two Zs. And so now it feels like, okay, maybe I'm just swinging the other way. It feels very non-classical.
But I mean, this people talk about this chiral algebra, right? Chiral algebra associated with any good theory. So they have singularity all over the place.
Yeah.
Right. But those are protected objects. They are you compute them one loop and then for any coupling they are the same. It's not like they're coupling dependent.
The algebra.
The algebra, the entire algebra.
I see. Yeah, so maybe it's okay.
Yeah, I mean, singularity is there, dictated by anomalies, but that doesn't mean that we should have pair of this lifting. It can make a pair of lifting, but it doesn't mean that we must have such pair.
No, but you just get worried that there may be like not just two derivative terms, but n derivative terms in the supersymmetry. Like the point here was that there was like a two derivative term in the supersymmetric transformation. Maybe now there are higher words. Okay, maybe not, but it was.
Okay, so having that in mind, today our goal is to construct new cohomology classes which are not of graviton type at wall border or at tree level cohomology. So now I will talk about what do I mean by which are not of graviton type. So in the gravity side, the BPS graviton states or all perturbative particle states, you can define it at the free level when G Newton constant is 0. Okay. Then one can find local BPS operators in super-Yang-Mills due to such states at n equals strict infinity. And the nice thing about these states is that when you construct them in n equals infinity, they exist at arbitrary finite n. They are BPS at arbitrary finite n. And this we call the graviton cohomologies. And in the gravity side, there are also the supersymmetric black holes which carry e to the n squared number of states, meaning that there should be e to the n squared number of BPS operators in the dual super-Yang-Mill case. So we can say that there should be extra BPS operators at finite n, not of this type, which are only BPS at certain n. If it is BPS at arbitrary n, then they will be included in these graviton cohomologies. So in order to capture this e to the n squared number of freedom, we should have the extra BPS operators at finite n. And it should be BPS only at certain n, not n equals infinity. And this can be done because of the trace relation between the matrix field. We have n by n matrix field, and if you have n number of them or larger than n, then there can be relation between the matrix. And this kind of relation, we call it as trace relation. And this will make such operator BPS only at certain n. And I will call these operators as, yeah.
So sorry, I understand that sentence. Correspondingly, there should be order each.
Yeah.
How does it follow from there that there should, or maybe, is there an independent statement that only at certain n you get BPS?
Yeah, it is a bit confusing part. So suppose that you have e to the n squared number of operator at certain n, and suppose that it is BPS at all n. Then you will have infinite number of states at n equals infinity. But we already constructed the states at n equals infinity. So this should not be the BPS operators at n equals infinity, meaning that they should be BPS states only at certain range of n. Yeah.
Yeah, so at infinite n, there are no trace relations, right?
There are what?
There are no trace relations.
There are trace relations at finite.
Sorry, at infinite n.
Yeah.
There are no trace relations, right?
There are trace relations.
Even infinite.
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 Yeah,
Infinite. No.
No trace relations. But at finite n, you are so there should be no black hole states at infinite n.
No.
But so, like, why are you assigning these black hole cohomologies to the four filter states? Because, but we do know that there are black hole microstates at infinite n as well.
No. When I say infinite n, if you first set n equals to infinity, you will consider finite energy states at n equals infinity gauge theory, right? You don't want to have the states with infinite energy. What we call black hole is that which has energy proportional to the n square. So you have to scale both n and energy in certain limit. So that is why we start from the finite n and we want to go to the large n. But if you start from n equals strict infinity, you cannot find any black holes or something.
So this argument that there should be new states, I'll tell you how I would have. I would have made it, let's count the number of supersymmetric gravitons. That grows like the number of states in a 6-dimensional gas.
Yeah.
Because you have 3 phi's you can put and 2 derivatives. So it's like 5 momenta, and that's how 6-dimensional theory works. So it grows like the number of states in a 6-dimensional gas. So the number of states, in some of supersymmetric states, in the supersymmetric gravitons, grows like e to the power 5 by 6. The entropy grows like e to the power 5 by 6. Because in any 6-dimensional theory, that would be true. And now I said E is equal to n squared, and I get n squared to the power 5, e to the power. The entropy is n squared to the power 5 by 6, which is smaller than n squared. Therefore, but we know that are supersymmetric. Therefore, they must be.
Yes, so we should have extra states, and they will remain BPS only at certain n.
So this is just saying that if you just count the letters or whatever at weak coupling,
The gravitons.
Graviton.
The gravitons.
that's what you mean by gravitons, right? Everything you can make. By gravitons, do you mean
Chiral primary is a multi-trace of chiral primary.
okay, also the multi-trace.
Yeah.
Of the chiral primary.
Yeah.
Trace xi, xi,
Yeah.
That the descendants and multi-trace.
Yeah, because the gas will keep the multipart.
Yeah.
Okay. If you keep all of those, then you don't hit the black hole number of states.
Yeah.
No.
You miss by a large amount.
Yeah.
Okay, I see. Very nice. But how does it follow that?
But we know that there are supersymmetric black holes. The index reproduces them.
Index reproduces them.
So that we know that there are enough states to count for the supersymmetric black holes. So we know that there are e to the power n squared states, but the gravitons count only e to the power n squared to the power 5 by 6. So there have to be new states.
Okay, but just to connect it with what you were saying, so the point is, if you take n squared to go to infinity first and you count, which is the graviton count, then you will hit some number of states.
I find that wording confusing because you want to count it at energy n squared.
Yeah.
So I mean, maybe that's what you meant. I mean, just if you count the traces, but it's energy n squared.
Yeah.
Phrase the problem. Okay, I had zero or weak coupling already that way.
Yeah. So some of this may be lifted and so on, but
it's already small.
It's too small. So
So even with lifting,
Yeah.
it's worse. So I see.
So as I said, these graviton cohomologies remain BPS, meaning that they have zero anomalous dimensions at arbitrary n. So this is the behavior of anomalous dimensions. So because of this behavior, sometimes we call it monotone cohomologies. And these black hole operators are in the BPS spectrum only at certain range of n, and it'll be non-BPS at larger n. So because of this, we call it as sometimes fortuitous cohomologies.
For the lack of monotonicity, you need a little more, right? There, don't you need to say that if you take the black hole states and you try to now take n to go to infinity,
if you take this, go n to the infinity, then this has infinite amount of energy.
No, I agree. These states are not there.
Yeah.
But therefore, they should not be there for all n. If they existed for all n, there's some argument like this.
The ones that exist for all n are multi-gravitons. The rest are specific to your value.
Yeah.
Because if they existed for all n, they would exist for n going to infinity. Those are your
Yeah.
Okay, nice. Okay, interesting.
So we have two kinds of operators, monotone and fortuitous operators. So let me show you how to construct this monotone graviton cohomologies. We'll start with single trace cohomologies at large n equals infinity. Then we start from the chiral primaries, which I mean the symmetric trace of scalars, n number of scalars. And then you can construct superconfound descendants of these primaries by acting fermionic generators commuting with our chosen supercharge. And these operators can be arranged into the short multiplet of this commutant subgroup, which is called Sn. And it has been known that they are absolutely protected from zero coupling to the infinite coupling. So these operators are there in infinite coupling. And for example, in S2, the conformal primaries is given as this. You have trace phi phi and also phi lambda, bilinear, phi psi, lambda psi, and so on. And then you can multiply these single trace operators to those multi-trace cohomologies at large n. And these correspond to the single and multi-particle graviton states in AdS5.
Sorry,
Yeah.
graviton states cannot become anomalous.
Yeah, they are absolutely protected. Single trace. And if you go to finite n, as I said, the formal construction give cohomologies at arbitrary n. But the thing is that they are not all linearly independent. The number of independent operators reduce due to the trace relations between the matrix field when the number of fields become larger than n. For example, in SU2, the chiral prime, let's consider the chiral primaries. You have trace x square, y square, and x, y, y, z, z, x. And if you consider trace x square times trace y square and compare with trace xy to the square, the difference is nothing but the Q exact operator, meaning that they are actually the same operator. So at n equals 2, these operators are the same. The number of independent operators reduces due to the trace relation. And actually, these are also well known from the dual gravity side as the stringing exclusion principle. In AdS5 gravity, if we put large energy to the gravitons, it is known that gravitons are polarized into the D3 brane giant gravitons, reducing a low number of states on that. So these kinds of BPS states are well understood, even at finite n, for the graviton operators. But as said, there should be some other types of operators responsible for the black hole degeneracy. So this I will call the black hole cohomologies, and now I want to explicitly construct such operators.
Can you explain this string?
So you have gravitons, and you want to put energy more than n. So it is a bit now far from the semi-classical regime. But then what happens is that this graviton will be polarized into the D3 brane giant graviton wrapping S3 in the internal surface. So this is not a point particle now. This is wrapped brane, D3 brane. And because on these three branes, you can construct some number of BPS states, and compared to the particle with n energy, this reduces a lot the number of states because of this polarization. So yeah, now I want to construct new type of black hole operators correspond to the black holes in the bulk. Any questions so far about the setup?
So suppose I have two gravitons that are both 160, annihilated by a particular 116 supercharge.
Mm-hmm.
They take the product of them.
Mm-hmm.
Then Q acting on the product is certainly 0. And n is large enough.
Mm-hmm.
So Q acting on the product is certainly 0.
Yeah.
And then presumably nothing can make this product out of Q also. So that is exactly protected. Is that under challenge? Is that statement correct?
Yeah, I'm not sure. I mean, for the single trace, it has been done, but if you multiply them,
if it's like an example, right?
n is large enough.
N is large, so there's no.
N is very large enough, then I think.
Then let's say we're doing finite things, N is very.
Then I think.
Yeah. So then the way it can not work is if actually, even though Q annihilates it, it might be Q of something.
Yeah.
That of course could happen.
Yeah,
Depends
yeah.
So that's the example there, right?
Yeah. In SU3.
Yeah, so that is clear. I understand that.
Yeah.
But I just, since people are challenging everything, I wanted to make sure that things I thought were true continue to be true. Okay.
Yeah, sure.
Wait, and then that Q acts like a derivative of all. That is, obeys the Leibniz rule. Is that of the challenge? For gauge invariant operator. Q on AB is Q on A times B plus
Yeah,
A times Q on B.
you mean the Leibniz rule?
Yes.
It is not true.
Even for gauge invariant operators?
Not true.
Not true. So what is wrong with the algebraic statement that Q anti-commutator AB is it some short singular? Q anti-commutator AB is Q anti-commutator A times B plus. So what's wrong with that?
But as you were saying, this one loop non-inversion kind of followed from that, right? At least the perturbative part of that. The perturbative part of the non-inversion statement follows from this picture. And that is not true, right?
Yeah.
These anomaly effects.
Yes, so there are two ways in which it might be not true. It might be not true at the level of letters, which would somehow be less serious because the letters were not gauge invariant things. Or it might be not true also at the level of gauge invariance. I wanted to understand what was the claim.
I think it happens even in the gauge invariant case.
Well,
I think it also happens in the gauge invariant case, though.
I like personally, I believe that the issue is whether there is supersymmetry preserving regularization scheme or not. So it seems that like mathematically there is no supersymmetry preserving regularization.
you're saying supersymmetry is a wrong.
Doesn't Greenberg work?
So Siegel proposed Dimrack regularization that preserves symmetry, but I think it is known that like only optimal node is preserved. But if you go higher order, then like it's not consistent.
Wait, but you're not saying that supersymmetry is actually not there.
Of course,
No,
it's not really there.
So might as well all go home.
No, I'm not saying that. I mean, if you want to act on a composite operator, then you need to regard.
The problem is that you're at the same point. That is the point. The short distance singularity.
Yeah.
If you took two separated points, then this would certainly be. I think so.
Yeah.
I mean,
Yeah. If we put, yeah.
I mean, how could it? Yeah. Okay. So up to that, so all effects are due to short distance singularity.
Yeah.
All samples are due to the short distance.
In terms of
Okay. That's what we know how to do. So.
Yeah.
Okay.
Yeah.
So everything is short distance singularity.
Yeah. Sure.
So if we were, so you're saying that all of this works at separated points, but now what about the limit as we get to 2.6?
Yeah.
That is.
Yeah.
What about the normal order? That can.
Yeah.
Okay. Right.
Yeah.
So you say in particular that for gauge invariance, this Leibniz rule may not. Okay.
So sorry, because I've used Greenberg for once early in my life. Two loops, I'm a little shaken. It actually breaks down the results. Is that true? So there's no supersymmetric regularization, no.
Again, I'm surprised by this. I mean, Heisler works in Greenberg. He gets this all loops to this one. What is this?
I don't know the detail. I just heard from actually she like he said that there is no typo constants in rap at higher. Sorry for
No, I mean, but there are people who are saying nothing's been shown, but like the Weiser Hamilton. Respect supersymmetry. It's constructed to do that. I thought it was consistent with the like that.
But by the Hamiltonian breaks like
Leibniz rule.
Yeah.
Leibniz rule is a matter of, from what I hear, it's a short distance. Right? But the question of whether this regulator preserves, that's a separate issue.
Sorry, I guess yeah.
Okay, so now we want to construct this black operator explicitly. So as I shown to you, this is quite an elementary problem. You have some number of fields, you know how to act Q on them, so you just multiply them and see whether it is analyzed by Q, but cannot be written as Q of something. So you can really start this program by your hands in the table. And I thought that I can solve the problem. I just write down all the operators from the lower orders.
Sorry, just one last.
Yeah, please.
You know, this operator was, I mean, at the level of just thinking of states on S3. If we were just looking at the action of states on S3, looking at Q acting on a state S3. Okay. Not going to the operator, not looking at the short distance singularity and so on. Can you translate some of your subtleties to that one? Sorry, sure. So I know this is a tangent from your point of view, but since it's come up, it's so interesting. Meaning, from Ungu's point of view, it seems to me that all the subtleties have to do with short distance singularities when you bring operators together. Okay. Now, all conformity theories are a state operator. Okay. So, given any operator, there is a corresponding state. So, it seems to me that what's happening is that in order to define that operator, you need to renormalize it. Okay. And because you need to renormalize it, you need to do some subtraction, blah, blah, blah. That's what's violating these classical rules. Okay. Now, now this has some translation to this state sort of state. Right? There you might have thought that if you just take the theory, you regularize it on a lattice, and this may be what you challenge. Then the action of Q is just what it is, because n equals one is a finite theory, so it's not. Yeah. So the action of Q just as a matrix is just what it is.
How are you going to ask the full question?
Yeah, I'm going to ask.
How do you ask?
I'm going to ask in terms of creation objects. So if I have Q acting on operator, then is it Q acting on this operator? Just take Q3 until it hits the back. But forget about Leibniz rule. I mean, there must be a translation of this subtle short distance singularity to this picture. It's presumably somehow the fact that finite matrices and infinite matrices behave.
Yeah.
And it would be nice to make that statement a little more precise.
Yeah. So I don't understand. What is the subtlety? I mean, corporately we have the singularity all the time. We talk about state operator proof. So what is it? I thought the subtlety is about the action of Q.
Yeah.
You want to see what is the effect of singularities on the action of Q, how it fails to obey this rule. Apart from that, what is the subtlety here?
Leibniz rule is just one thing.
Okay.
The action of Q on states, we thought we knew it was the classical action of Q. Just on fields. Because there's an action. You have a symmetry that preserves it, and that action is not being renormalized into the. So in this lattice action, if you couldn't make a lattice regularization that preserves supersymmetry, you would know what the action of Q was on all fields. Okay, and then I could figure out from that the action of Q on states, and this business that Q has to get renormalized. I'm trying to understand what that means in this. But how can lattice preserve? Yeah, lattice fun. So it was quote unquote lattice. Yeah, dimension regularization. Something that preserves it. I think that's the sign that we cannot do this properly in order to preserve it. But still, like, what did I? There's something to say about it.
You can't just, sorry, when you say the action of Q is renormalized, causing some, Q is a conserved charge, right?
Yeah.
Only the conserved charges, their normalization is a very secret objects, right? Because what identities tell you, if they are going to hold, this is the statement of supersymmetry. that you can't renormalize charges. So what exactly do you mean? Yeah.
You have QQ dagger
Is
this, and this R and J are quantized charges, so they cannot be renormalized, but anomalous dimension can be renormalized, right? They are just real numbers.
So therefore, so this charge is. I mean, like U1 charges and all that are never really normalized, you know. They're anomalous limits, but this is different somehow.
Yeah, dimension can be renormalized.
All of you know this, but somehow. It's strange.
Okay, so you can just write down all the operators from the lower order. So I just wrote down. I thought that I can solve this problem when I was a graduate student. So I just wrote down everything. And you'll find all of them are just graviton operators, even if you write down hundreds of operators. So this is a hopeless approach. So we need to use some other thing. So we need to use.
Hopeless in that you don't discover the additional states. So
Yeah. You need to go very higher order, meaning that it is almost impossible to write down all the operators unless you have infinite amount of time. So you need to use different approach based on the index. So as before, we will use the superconformal index. In today's language, this superconformal index will count the BPS cohomologies with -1 to the f. And you can compute it using the unitary matrix integral, as I showed you yesterday. So this, you can compute the number of total BPS operators with -1 to the f. And you can independently count the number of graviton operators at finite n. So you know the form of the graviton operators, and what you have to do is just check the independence of these operators at finite n. And using that, you can compute the finite n graviton index. And you can subtract this graviton index from the full index to get the black hole index counting only the black hole operators. That's what we're going to do, what we wanted to do. But the problem is that our problem is still difficult to analyze. So we want to truncate our problem into the sector with no derivative. Without derivative, our life becomes much easier. So then we should also not excite the Gaugino because Q action on the derivative will give you Gaugino. So we will not excite Gaugino field, and we will not also act derivative on the fields. Then we will have only scalar, Carolino, and field strengths. And these are the fields that is excited on the BMN matrix model. So we will call this subsector as BMN subsector. And the Q action rule on these letters are given as these. And this index over BMN cohomologies can be written as this. Then, since you don't have any derivative on them, the integrand is now just finite rational function. So meaning that you can explicitly compute by residue integral. So you can easily compute it to get a closed form expression from the index. And you can see that even in this subsector, they exhibit n-square entropy at large n. So even we focus on now some subsector of n phosphorus primary, there are black hole operators in this subsector. So this is a nice subsector. And for the illustration purpose, just a moment, I will unrefine all the chemical potentials to the T square. And there were some slides about counting the number of gravitons. We had some strategy, but as you can hear now, this is actively debating field, and somehow we now realize that our strategy was wrong. I mean, can be wrong. So, but the result is okay. So anyway, you could get the number of the independent gravitons, and in SU2 theory, this is a closed form expression for the graviton index.
Wait, why is the strategy wrong? I mean, the fact that you want to evaluate this, basically the index on multi traces, right, of these BPS primaries, get the graviton index.
No, this is 16 BPS.
Yeah, we'll consider its descendants also.
Yeah. So we have all the 16 BPS cohomologies. We want to now test the linear independence of them. when you do that, we use the eigenvalues, so we diagonalize all the fields then, but in some cases, it fails.
Is this related to all this discussion, or is there some different issue?
Related but different. Somehow it is involved, but I think it is different issue.
But as well, suppose here who was talking about some Grosvenor basis or whatever.
Yeah. Is that true? So using Grosvenor basis means that you diagonalize all the gravitational fields and make these matrices as polynomial. So counting the number of independent polynomials.
Yeah. So what is wrong in this? What's wrong?
If you diagonalize all the gravitational fields, so in this case it is okay, but if you consider some other gauge series, some gravitational operator just vanishes if you diagonalize all the fields.
So in SO7, if you restrict all the fields to the diagonal fields, then
you lost the operator.
Yeah.
Is that the same operator that recombines with this other thing?
Yeah.
So it's related somehow.
It's related.
Yeah, it's related, but in some other theories, it is not related to the lift. So there are some examples that this diagonalization doesn't work, but it is not related to the lift in some other theories.
It's very interesting. Then. But then, for example, in n equals 4, SU and n equals 4, this doesn't happen, right?
Yeah, that doesn't happen.
The fact that this doesn't happen should be clear. So one expectation you can already have that issue will not affect SU and n equals 4.
Yeah.
Okay.
So in n equals 4, it was okay, but there is no clear reason why this is okay. But anyway, we could get the number.
Sorry, can I ask a very immediate question? So the issue is finding the finite and trace relation.
Yeah.
And if you don't go into details, but when you say you will diagonalize, I mean, is the point that you're trying to simultaneously diagonalize all the
Yeah.
That's not clear that you can do that, right? Or
Sure.
Yes, you see, in for multi-gravitons, it sounded sort of crazy because a multi-graviton, a single graviton, at least in n equals 4, is traceless symmetrized size and then descendants. Let's forget about the descendants. So if you've got traceless, forget the traceless thing, you've got symmetrized phi's, then because they are completely symmetrized, there's no order.
Yeah. So for the enumerating purpose, it is reasonable to treat them as the diagonal matrices.
but you say and it works for n equals 4. But
N equals 4, SUN it works.
SUN, but not
It's clear that it works for SUN.
No.
It
It just work well for our case, but we don't know why it works well.
But how do you know your final answer?
You can be independent check. I mean, not only you can just look only metrics. Yeah.
Or SU2.
Yeah.
So, and is the question for where it might not work for the descendants or even just in the scalar set?
Scalar sector is okay.
Scalar sectors.
Yeah.
Yeah. So the descendants sometimes introduce some funnel symmetry structures, right? Yeah. So is that the only issue? Then I understand that one.
Okay, so for SU2, we have this closed form expression for the graviton index. Then we need to compute the index of our full SU2 BMN cohomologies, and this is the form. For your information, I just gave you the BMN single trace graviton in SU2. We have three kinds: trace by phi, trace by sine, trace by S. And then you subtract the graviton index from the full index to get the black hole index. It's written as this, quite a simple form. This counts the black hole operators in SU2 gauge theory in BMN subsector. And if you only find all the things, you can see that actually this index starts from T to the 24. So this new operator appears at level 24. That's a very high order, so you cannot easily write down from the lower orders. So we have three factors of the index, and I want to interpret it separately. So the second factor, okay, so the first factor, I want to interpret it as the genuinely coming from the genuinely new operators, which I call the black hole primary operators. The second factor is nothing but coming from the superconfirmed descendant of these primary operators. And the third factor can be thought of as the multiplying certain kinds of multi-graviton states on top of these black hole operators. You have the black hole operators, you can multiply arbitrary number of these multi-graviton states will give you this kind of infinity loop. So we have to account for these. And if you only find all the chemical potentials, you will find this simple series, meaning that you need to find unique new fermionic operators at each level 24 plus 12 n. Now we want to explicitly construct these operators. From this, since we are working on SU2 theory, we show you three-dimensional vector notation for the SU2 adjoint fields. Now this cross product is nothing but the commutator.
So is there a fair expectation that these black hole properties has to be fermionic?
So how? You are asking why this is fermionic?
Is there some expectation that it has to be fermionic?
No, it just turned out that it is fermionic. So at the level 24, we just found by brute force using computer. So this is the operator. So this V is actually nothing but the graviton operators. So you multiply two gravitons and then multiply with some triple fermions and contract all the indices. Then you will have this operator. So this third factor is actually not Q closed by itself, but if you multiply them and use SU2 trace relation, you can show that it is Q closed. And also not Q, and also you can show that this is not Q exact, meaning that this is genuinely new operators in SU2 series. So in some sense, you can say that it is most quantum black hole. Very smallest 10, smallest charge. Okay, so this is new type of operator correspond to black hole. And
we know this will not be lifted by anything because it is needed for the index. Is that right?
Yeah, so this is expected from, so expect index tells you that there should be some states. And after the computation, you can confirm that there is no UP pair operator with this. So it should be there. It should not, yeah, it is not like this. So this will be at the strong component. Yeah.
So why not there be some other operator as well, other fermionic and bosonic operator at that level? And then the pairing can happen between this and the other bosonic operator.
No, this is the only operator in this sector. At volume level, this is the only operator you can write down.
Is the worry, sorry to ask this naive question, that at higher group some other operator descends here and then they can.
You are saying that some non-BPS operators at free level becomes BPS because of the higher level.
I mean, I'm asking since various things are.
That I have not seen.
That was not at least my worry. I was just in perturbation. Small problem. But sorry, this sector business. This restricting to this sector, is there some charge way to restrict to the sector?
Sorry, is there some
This you're not in this BMN sector for this calculation?
Yeah, BMN sector, right?
And is that restriction to the sector because of some charge? Can you restrict in some invariant to the sector?
You mean tuning some parameters in the theory, or
what I mean was that all states of particular charge are in this sector.
No. They are as a sector with same charges in the full gauge theory.
So then how do we know that something from there cannot, something from some other sector cannot come? I just to know whether
this one loop Q action is closed in this.
Yeah, but since one loop is being challenged, I'm just wondering about how we know whether this how.
So the vertex of conversion was this, like there is only one vertex converging in the loop.
In the full at this charge.
Yeah. Even at this charge, in the full sector there is only
So then that's clear.
Yeah. So this will be there even at the strong coupling. Yeah. So this is really the quantum black hole.
So we didn't, this using this BMN thing was a convenience.
Yeah. To make our computation simplified.
So you guys at T to the power 24 looked at the whole 116 DPF factor and found that they are lower than.
Sorry, I cannot.
So you guys looked at T to the power 24, the 24th energy, the whole 116 DPF sector, and found that this is the only port filter.
Yeah.
With all the derivatives included, there are no other port filters.
No.
At this charge.
Yeah.
No, but even if you see that at this initial charge, there is only -1. Then also you are done, right? This next count. You have the operator, you compute the charges that commute with Q, and those charges look at the index, full index, and you see that there is -1 coefficient. Then also you are done, right? Something, this or some other thing has to be protected.
But it could be something completely different. Could have different actual charges. Same initial charge, but on these.
So there is only one, so you can believe that this will be there at strong coupling. So, and then I showed you that there is a tower. Can we construct them all? Yes. So basically from O0, you multiply some composite operators and make it Q closed. You can make some complicated operators, but you can believe me that it is Q closed, but not Q exact.
So is this mechanism of opportunity is that you act with Q on this operator, and if you keep in general, then you get a non-zero right-hand side. But for a particular value of n, because of trace relations, that sign vanishes.
Yeah, in principle, you can check in that way, but in this case, you first check this is the cohomology, and then you check that this is not the gravity. Not the graviton.
No, but I'm saying
it cannot be written as the graviton cohomology, meaning that it is perfect.
Right. But is it that the Q action vanishes due to trace relations only?
Yeah.
Right? Not for general.
Yeah.
Now when there's another place where these trace relations came up when you talk about stringy exclusion principle, right?
That is different thing. So that reduces the number of states. Trace relation makes.
Yeah, that's what I was going to ask. So it seems that these two things are related, right? Meaning the thing, the stringy exclusion principle, the thing that is setting to 0, is the thing that is giving rise to these gravitons. So I'm worried I'm just confused about the counting, because this you need a lot of them, right? Or is it the same as this?
What do you mean by all?
N squared, right? N squared of them, n squared of them. And is the number of relations also equal to n squared? I mean, it seems related. Trace relations.
Trace relation, number of trace relations. That is very difficult question. I cannot give you the answer.
That's also n squared.
But I think like number of trace relations for gravitons is much smaller.
Yeah.
Number of trace relations.
Yeah, of course that is true.
Just because the number of gravitons.
Yeah.
No, I mean for the full relations, because the opportunity is because of all the relations.
Right. He is asking the number of full relations.
That should be very large.
Yeah, that should be very large.
I mean,
in order to account for the black hole entropy.
But if the question was why isn't the number of liftings more than the number of gains? If that was the side of the question, I mean the number of liftings can only be in the gravitons, which was itself very simple.
Yeah.
Gains can be in this bigger place.
Yeah. It should be. Yeah, sure.
Right. Well, that is one part of this question, but the other, the first was that when you talk about matrix simulations, it's somewhat more tractable. It's just mathematical. So maybe one can try to understand this computer space just from matrix simulations.
Yeah, sure. And one funny thing about this tower is that if you pick any of the two and multiply them, they become 0 because of the Fermi statistics. And these account for the whole SU to BMN index. So we basically we explicitly construct all the black hole operators in the BMN subsector for the SU to gauge theory.
So, and when you said that this we sure is there, also the multi-gravitons around this we sure are there.
Yeah, you should multiply some graviton on top of that. Yeah.
And those also it's not just a one-loop thing that we know somehow absolutely that those exist.
That I'm not sure. That we don't know. Well,
It's qualitatively important because the question of whether gravitons continue to be supersymmetric around black holes is an interesting question.
yeah.
And not totally clear. And it would be nice to know for sure that this multi-graviton spectrum is protected.
Yeah, sure.
Around that.
So the bottleneck here to do the graviton homology calculations for the full index.
Yeah, so full index, there are other sectors, so we don't know whether this will be lifted or not.
Even for one of them, can you say, just to know for sure that there is one graviton? The danger is that if you solve a gravity wave function, at the horizon it becomes sort of singular or something. Maybe singular and dying.
Yeah.
And maybe that's not legal. Like you guys solved in your way. Right? I can't remember who was on what.
Yeah, I think you are talking about this part. Maybe I can tell you a bit later. The singular part.
Just to understand, it's so hard to simply take a black hole diagram and introduce a graviton.
Yeah.
You know all the supercharges and so on.
Yeah.
It's so hard to check whether a single graviton can preserve.
Well, some subsequently days. I don't know who was on that.
Yeah. Sure.
Both of them.
Yeah.
It's very tricky, is it?
Yeah.
You'll come to it sometime.
Yeah.
No, but I think the basic one is very simple. You can solve the Killing spinor equation for the graviton to get a solution. Now the question is that solution legal? Okay, it's going to be normalizable at infinity. That's fine. The question is what happens at the horizon.
Yeah.
Now what are the rules?
Yeah.
If this thing is non-analytic at the horizon, but decaying sufficiently fast, is it allowed?
Yeah.
That is basically the rules you guys apply. Right? You said that if it's decaying sufficiently fast, you will take it.
Yeah.
Totally clear to me because in string theory there are alpha prime corrections. So something that is decaying like 1 over x to the million 0.5, you take million derivatives, it blows up. So the rules are not totally clear to me. So it would be nice to have independent block.
Yeah, that's true. So we have constructed these operators, and you can ask, can we have some interpretation of these operators? There are some interesting things, but today I want to talk about the following things.
So just press on that. Just the first graviton state.
Yeah.
Can one look at that carefully?
Yeah.
And convince oneself that must be there. By looking at the index, by doing various.
Maybe, but the problem is that when you multiply some graviton, it means that the charges will be higher. Then you can write down many number of states. So the computation is a bit difficult. But in principle,
just one.
Just one more is difficult.
Okay.
really. I mean,
level, why don't you just compute the index?
Index sees that operator, but it doesn't mean that you can write down the only such an operator. Yeah.
So, but were you interested in particular form of this operator?
Yeah, I wanted to see that it looked like graviton pressing. If it was another black hole state, independent black hole state, that's good.
So I want to study some properties of these black hole operators from the semi-classical black holes in AdS. So in order to do so, we will see, we want to consider the finite energy excitation outside the horizon and see whether it is absorbed by the black holes and whether we can have some stable configuration. So we have simplest BPS black holes in AdS5 is the Gutovsky-Rel black hole parameterized by one parameter Q. And you consider the bosonic pro-particle dual to carry a primary N in the black hole background. And you can find rotating BPS solution outside the horizon only when the angular momentum exceeds some combination of its charge and black hole charge. It can be intuitively understood. Angular momentum is small, then it can be there, but if angular momentum is large enough, the centrifugal force can balance the gravitational force, so you can have some stable horizon. And you can promote this to the wave picture. So we study a small complex scalar field in the Kyler multiplet on the black hole background, and you can solve the BPS equation of this complex scalar field. And you find this solution, And here, this angle-dependent part is nothing but the usual derivative factor acting on the conformal primers. And this is the radial part. And you can see that at the horizon, the solution remains finite only modes satisfying the angular momentum quantum number is larger than certain amount of charges. So, meaning that
finite, but since this product, it's not always analytic. It's not
analytic. So, yeah, as I said, if you consider the higher derivative, higher derivative correction, there can be some problem which we don't know, but so we just studied in the probe level in the Einstein range.
It could even be that when you look at this non-linearly, that smooths out the signal. Because you're just doing linear. But whatever, I mean, it would be, this is very complicated kind of what the rules are as well.
So this can be also intuitively understood. So for when the angular momentum quantum number is small, the fields will be more likely. I feel in the black hole background, the central region is hidden inside the event horizon, and when the field with lower angular momentum quantum number, its profile is centralized, focused on the center, meaning that it will be more likely swallowed and give you back reaction to other complicated configuration. But with field with very large angular momentum, they will rotate outside the horizon and can be superposed with small bang reaction. So this is the thing, we can construct some supersymmetric Harry black holes.
Can I just ask one thing? You guys will all hate this, but there are famous issues about exactly at extremality things diverging at the horizon. The stress tensor diverges and so on. And one way, not for BPS problems, but just one way to deal with it is you keep the black hole up a little bit, and then everything is sane, and then you follow the state. Now, I don't, this probably not work here, but anyway, that's how most physical questions are dealt with, right? If there's some pathology at extremality.
Yeah, but here the question is about counting BPS states. It's just a little bit non-BPS. It's different.
It's a little bit non-BPS in another parameter. But okay, I know you guys will get this.
It's plausible. Everything you thought has been quite challenged,
Sorry, yes.
So we found nice picture in the gravity background up to that subtlety that only with fields with large angular momentum can be superposed on top of the black holes. So my question will be whether can we understand this from the CFT operator spectrum in SU2 theory. And that is true. So if we multiply the Carrier primary graviton on top of,
What is the question? So can we
understand this kind of behavior from the CFT operator spectrum? So I showed you that
existence of hair.
Yeah. So hair with small angular momentum cannot be filled with small angular momentum cannot be the hair of black holes. Only with large angular momentum that can serve as the hair of black holes. So if you multiply the chiral primary gravitons, which have zero angular momentum, on top of this black hole operator, you can explicitly show that it is Q-exact, meaning that it is lifted even at volume level. So they are not in the BPS spectrum. And then you act one more derivative on them. It is also lifted at volume level. Okay, then what if we act 2 or 3, and they are in the BPX spectrum? So this is the qualitative accordance with the hairy black holes in AdS5 we found.
And you say qualitative, it's because you had predicted some certain, you needed some particular L, but you can't match that value, right?
Yeah.
N equals 2.
Yeah, N equals 2, so you cannot match the threshold level, but anyway.
That's large enough.
Yeah.
And once one L works, all L is larger than that also. Yes. So it's very beautiful. It sings like it is.
Is this true that 2 of SU2? Is this true that 2 of SU2 why you need to have 2 derivatives to get a Q closed operator?
I mean, rank and the number of derivatives are related.
No, I don't
think so. I don't think so. Because it depends on the gravitons you consider. So here I only showed you the scalar gravitons, but if you consider another gravitons, the number of derivatives you needed becomes different.
For SU2.
Yeah, even for SU2. So these are in qualitative accordance with our hairy black hole picture. And one funny thing I can say you here is that you can also consider some other graviton, right? And if this picture should be right for also for the other gravitons, for let's say from the threshold level, if you act enough number of derivatives, there should be in the BPS spectrum, right? But if you assume that should be true, you can find some would-be pair in the spectrum, even at volume level. And testing whether they are really at the BPS spectrum will be interesting.
Sorry, please, can you say that one? Just repeat what you said, basic.
So, as you said, if you act large enough number of derivatives on top of the gravitons, we think it will be, I mean, for the Carrier primaries, it is there, but if you consider some other things, we think it is in the BPS spectrum, right?
Yes.
But if you assume that should be true, then there should be would-be pair BPS test, would-be pair BPS test, so that it cancelled to give you 0 in the index. So whether this is really lifted or not will be an interesting question to check. Okay, so I explained hairy black hole primaries, how to construct hairy black hole primaries, and using that I explained the indices up to certain order. And you may ask, are they all? Of course not. If you go to high enough order, you cannot explain all the indices using these hairy black hole operators using our threshold operator, meaning that you should find some genuinely new operators we don't know yet. So this is the story for SU2, and then you want to go to maybe SU3, and SU3 the situation becomes more difficult. So this F0 is analogous to what I showed you for the SU2. SU2 we have one tower, right? One fermionic tower. But for SU3 now we have several towers. And the nice thing is that this first fermionic tower can be understood as the black hole superposed by this dual giant graviton things. It is beautifully explained in this paper. So this is related to the dual dressed black holes in the gravity side. Dual dressed black holes. Sorry, black hole dressed by dual giant gravity.
Oh, I see.
For the hairy black holes I showed you here is the dressed by the hair with large angular momentum, but you can consider the hair with large charge. And this tower is responsible for that.
So why can't you have dual dressed solutions in SU2 case as it?
Why don't we have?
Why shouldn't you have? I'll tell you why you shouldn't have. You shouldn't have because you see, if you have dual around it, then the flux inside is one unit.
Yeah. If you have dual giant one, yeah, this is a domain more for the RR flux. For in SU2, you don't have any.
Yeah. So why you should have expected qualitatively graviton dressing already from SU2. You should only have expected dual dress from SU3, and it works so beautifully.
Yeah,
At least that's one unit.
Yeah. So this reduces the RR flux, so SU2 you cannot have such configuration. And yeah, I'm running over my time, so I'll not explain how we. So we have some ansatz using the trace relations and relational relation, and using that we could find these complicated horrible operators in SU3. This is the threshold black hole operators in SU3.
How do you use some mathematical program?
Yeah.
It's not humanly possible.
We use Mathematica very much.
Use Bocol too.
I could.
No.
Paper. Like this is very challenging for.
Yeah, this is not paper with some other person, but we did not use Macaulay, we use Mathematica and some supercomputer efficient. So,
I use singular.
yeah, singular we use, yeah.
Give us kind of
Yeah.
It's just 1 minute, I'll give you my experience with Sunjin. We're on a Zoom call and we're thinking, perhaps this will happen. The 2 minutes later, he has a graph that says it happens. Different level of.
So somehow we constructed this, so please believe me, this is Q closed, but not Q exact and not graviton. But here, U, V are the graviton operators. This is the chiral primary and component, this supercomponent descendant of them, and on top of that, you have many number of ion size. So, but we found this operator, but still we don't know the usage of this operator yet. All I can see.
So these are like the core operators.
Yeah.
The things that are not addressed.
Yeah. Maybe we can consider some dressing of these operators. Just like SU2, but yeah, we haven't done much. And
by the way, so if you do this full index minus this thing, the graviton index, the remaining stuff cannot. You have the full accounting of that using this just black holes and gray galaxies. This black hole.
You mean in SU3 is whether we can have this gray galaxies and your dress black hole things?
I mean, does it account completely for leftover stuff?
This is account by the your dress black holes, and you're asking whether these can be right. These other things.
No. I mean, just when you take the difference of these two indices.
Yeah, this is the difference.
Okay, so you are accounting for everything. Okay.
Yeah.
Sorry, one more question. Is there some distinction between like from the operator spectrum of gray galaxies and the, let's say, dual DTBH? Can you distinguish from the CFT?
Sure. When you have the gray galaxy, it means that you have angular momentum tower. When you have dual dress black hole, you have R-charged tower. Holographic tower. This is the Colson-Klein tower.
So at some point, I suppose, so at some point it should be possible to just have the gray, the dual also start spinning.
You mean dual giant graviton spinning?
Yeah. I think in AdS, if you think of the dual giant graviton as a primary, we could take descendants of that.
But this rotation is isometry of this ring. Do you know what this? Can you have angular momentum on there?
It should be possible. I think what will happen is that you make a bump on it, and then that will do it.
And you're considering some excitation on them?
Yeah, I was saying just from the fact that since it's the primary, there are descendants.
Yeah.
So, perhaps you cannot distinguish that from adding new gravitons.
Yeah, maybe.
Or just new gravitons, they probably, from your point of view, iso.
Yeah, maybe. Yeah. So you are saying that now hair can have both charge and angular momentum.
Yeah.
If you consider that kind of hair, then you may not distinguish.
But are they two different solutions? You have bumps going around and also separate gas going around.
Yeah, I suppose at least at large end, duals are very large. So they angular momentum for gravitons that have very large charge. But you could also have had angular momentum for gravitons that have small charge. No, they're all gravitons. So different kinds of gravitons.
So if the operator that you showed this is if you add with derivatives, what you have to do is
Derivative.
Yeah, like the case you added derivatives for the SU2 case as well.
You mean the gray galaxy case, like
the gray galaxy?
Yeah, we think that will appear in the spectrum, but the problem is that we cannot compute the index up to so higher order. So,
but let's say 1 or 2 or 3 derivatives will be.
Yeah, I mean, going one charge higher is very difficult. Okay.
realize I'm confused about something basic about dual giant gravitons, which is, I thought they're fuzzy or whatever. They're D3 brains wrapping S3s on S5.
No, dual giant is AdS.
Oh, that's what I'm confused about.
Yeah.
Duals are in AdS5.
Yeah,
That's why you're saying it's an isometric.
Yeah.
Okay. Thank you.
So you may ask then, can we go to SU4? And the answer is no. We could compute the index, but explicit construction is, we couldn't do that. Maybe some more technical people can do that. But the funny thing is that, so for SU2 and SU3, the threshold operator is always a singlet under the R symmetry and rotation. But now the threshold operators are charged, non-trivially charged under the R symmetry. This is one difference in SU4.
So in your earlier time, you had some paper with Seok that was too appear. What part of this was it that?
Too appear?
Right at the beginning of your talk.
Okay, yeah, I have that in my future section. So
I see. It's the future.
So no, the different thing. So, yeah.
So in your last slide, is the difficulty in computing exactly Z graph?
Exactly what? Z graviton. That is also very difficult. I mean, so it's basically analyzing the linear independence of finite number of vectors, but if you have very lots of numbers of vectors, the linear dependence test is very difficult.
For SU4, it's undoable.
Well,
I will not say undoable. We cannot do.
Is this development stuff useful for that?
Yeah, here they need diagonalized matrices, right? I mean, it very works with development.
But the general mathematical structure that he works with may well.
Because those are true, that structure is true for any sort of ring that is, free ring modulo some symmetry, right? And then here, if you have diagonalized stuff, you would mod out by what, y?
Yeah.
Yeah, so be a discrete version of that.
Well, let me conclude. Today, we studied classical comodules of BPS operators n equals 4 SUNs for Yang-Mills. And even at small n, I explained to you that we can distinguish operators from gravitons and the rest will be dual to the quantum black hole microstates in AdS-CFT. And in SU2, we constructed an infinite family of black hole operators, and we studied the Hare behavior on top of these operators. So only the conformal descendants have enough angular momenta can grasp these black hole operators, and we provide a gravity interpretation of this phenomena studying graviton hairs particularly superposed with non-hairy black holes. And at higher end, I did not provide, but our paper provided as such for the construction of Q-closed operators. And for SU3, we found many Taurus states, and some of them are explained by dual-dressed black holes. And we also explicitly constructed new, genuinely new core black hole operators in SU3. So this is a cartoon of what we have done. So we have 16 BPS operators. Some of them are graviton, some of them are black holes. And among black holes, some of them are core black hole operators. And some of them can be explained by dressed black hole operators. And dressing can be in two ways: large conformal descendants of graviton, large angular momenta, and some are dressed by large dual giant with large R charges. So we have various future directions. You may ask higher charges or higher SUN if you have very good technique. Or you can consider some less supersymmetric generalizations and consider some implication of Higgsing and S duality. And this is the S thing. So we consider some Klavanov-Witten theory, and it is related to the n equals 4 theory by Higgsing. So you can ask whether in this procedure, this cohomology spectrum, how it changes under this Higgsing procedure. Or we can consider some class S series and think about the S duality, how the S duality works in this series, similar to the works in SO7. Yes. And you can consider some other space-time dimensions. Recently, these people consider 3D ABJ vector mode. One other thing you can consider is that since we have some operators, you may want to study some OPEs or correlation function between them and study some complexity or chaotic behavior of them to study the black hole physics. And also, we saw that the operator spectrum shows the states dual to the BPS gray galaxies or dual to rest black holes. So related to the yesterday's talk, can we construct some large cell, for instance, the index dual to these hairy black holes? That will be also very interesting direction. Okay, that is for today's talk. Thank you for listening.
Had a quite a bit of discussion, but one or two questions.
A very nice question. So in one slide you showed that if you take product of two, for SU2 case, product of two, for Twitter state, OL dot OL is 0.
Yeah.
Due to this Fermi statistics.
Yeah.
But these two operators are at different initial charges.
Yeah.
So why are you saying that?
Of course, these two operators are different operators, but they are composite operators, right? They have they have some number of fermions inside that, some number of fermions inside that, and if you multiply them, you have large number of fermions and it becomes 0.
Sorry, I'm asking this so late, but just to first ask, 116 BPS means they preserve 4 supercharges? 16 over 4? No, 2 somehow, right?
One Poincare,
32 by 60.
Yeah, one Poincare and one conformer.
Okay, 32 by 6. Okay, so now my question is really this. Okay, so this is beautiful, and of course, the N equals 4 theory is the canonical example of holography. But if the idea is just to be able to follow states which become eventually black holes in great precision, would it be easier to do it in a theory where the black holes have more supersymmetry?
Black holes and more
Like what I mean is some example, I'll have to concoct it, but can we have examples in AdS where your black holes preserve, more than, so here you were preserving 2 supersymmetries in the end. And would it help if
you are considering black holes preserving more supersymmetries than 2?
Yeah, is it possible? Of course, in first place it's possible. I don't know the story.
In AdS, recently there is a paper arguing that black holes have preserving supersymmetries more than 4 is forbidden.
More than 4 is forbidden. I see.
4 is
4 up to
4 is threshold, but we don't know. I mean, so far only black holes preserving 2 supercharges has been known. 4 supercharges we don't know.
So it's not. Thank you.
I mean, if you look at the known 116 BPS solutions, if you take special corners of them that, so where their charges are such that they will also preserve an extra supersymmetry. Okay? But every time that happens, they develop.
Yeah,
they're 0.
Yeah, they vanish.
Area.
The area vanishes.
Yeah,
if you look at the known class solutions,
non-solution vanish.
It's very striking. The boundary of the existence of solutions is in answers.
And some people were trying to find this genuinely new black holes preserving 4 supersymmetries, but I haven't heard any success.
And if you take the 4 supersymmetries to be the chiral ring at least,
no,
we know that it's impossible because
no.
we can just diagonalize at least the one ring. So the number of states is N.
The only possible sector is the Shor sector or McDonald sector.
Okay, let's find some different.